Hello everyone, my name is Sev Kaminsky, and today we'll learn how to program an FPGA chip from using a traditional approach to programming an FPGA to using a more intuitive and graphical approach. So before we look into programming an FPGA chip, let's actually look into what an FPGA chip is. So an FPGA chip stands for Field Programmable Gate Array. So what that is essentially a piece of silicon that has a number of inputs and outputs. And what this piece of silicon has is basically billions of unconnected logic gates. So this can be simple logic gates such as your AND gate, your OR gate. It can also be arithmetic blocks such as multipliers, adders, and so on. So the cool thing about an FPGA chip is that these gates are not connected. So the user can define the way these gates are connected. So basically, a user can create a program in software, and then the compiler will create a hardware implementation of the program. So for example, instead of creating or manufacturing an analog filter, you can actually create a digital filter that has the same functionality, define it in software, and then the compiler will implement that filter on the FPGA chip. So this is really powerful. So at the very basic, the user basically defines inputs such as A connected to B, as well as the functionality that he wants to implement on the chip. So for example, at the very basic, we just want to add two inputs. So then, once the user has defined this functionality, the compiler will take a look at this FPGA chip, take a look at what resources it has, and will basically take the two inputs A and B, connect it to an add block, because we would like to implement an add functionality, and then route that inputs to an output C. That will give us the sum of the two inputs. So when it comes to programming FPGAs, traditionally people use hardware description languages or HDLs. So let's take a look at an example of an HDL program. So an HDL program is basically a piece of source code, typically with a VHDL extension. So let's take a look at this piece of code. So here's an example of an adder block written in VHDL, which is a hardware description language. So you can see for this specific implementation, we define all the inputs and the outputs of this adder, as well as the functionality of what the adder does. So in this case, let's say we've defined a clock, a reset signal, as well as our inputs and outputs that we're trying to add, as well as the size of those inputs. In this case, it's a 64-bit number. So once we've defined the architecture, once we've defined the inputs and output ports of the adder, we need to define what the adder does. And this is part of the architecture block. So in this case, what happens is on the rising edge of a clock, what we'll do, we'll take the ports A, B, C, and D and add them up to give us the C add out result. So you can see that this is a rather simple piece of code that basically implements rather simple functionality. But you can see how many lines of text we had to write just to implement something very simple. So another way of programming FPGA that I would like to show you today is using a program called LabVIEW that can do the same thing. Basically, it can create a software-defined program for your FPGA chip, but it does so in a graphical, user-friendly way. So let's take a look at that. So let me go ahead and open up LabVIEW. Alright, so now that LabVIEW is open, to start programming an FPGA chip, we need to create a project. So you click on Create Project. So for this very simple example, what we'll do is we'll create just a blank project. This is the simplest case. So so we see the blank project here. So next thing we need to do is we need to select which FPGA we would like to program. So we'll right click and add an FPGA target to our project. So there are a number of FPGAs that you can select from, but we'll select the 7976, which is just a Kintex 7 FPGA. So once the target is added to our project, we can start creating a program for that FPGA. So we right click on it and select New VI. So VI stands for Virtual Instrument. That is how LabVIEW is basically, that's the file name that LabVIEW is using to for source code. So any source code in LabVIEW has an extension .vi. So here we have a front panel of our source code, which basically has the graphical user interface that allows the user to interact with your program, and the block diagram that implements the functionality that you would like to have in this program. So in this case, what we'll do, we'll create a very simple adder. So we can right click and open up the palettes. So the palettes have a number of functions that are available to the user to select or add to their program. So in this case, we'll just use a simple add gate. And then we'll also create two controls that we'll use as inputs to our add gate. So one of them will be X, the other one would be Y. And then we'll have an output indicator with our result. So what we'll do, we'll also change this to an integer data type, for example, in I32. And we'll also be running this program inside a loop, because we'd like to continuously calculate the sum of two inputs. So I'll add a while loop around this piece of code, and I'll add a stop condition for this while loop, which would be just a user button called stop. So you can see as I add elements to the block diagram, they show up on the front panel. So in this case, I have two controls and one indicator. All right, so before we actually compile this program down to an FPGA, to a hardware implementation on the FPGA, we would like to simulate the behavior to make sure that everything behaves as we expect it to behave. So let me go ahead and save the project. So to be able to simulate the behavior of this VI, I need to switch the FPGA target to simulation mode, so then I can test out the behavior of this code. All right, so then I go back to my front panel, and I click the run button to actually start running or executing this code in simulation mode. So in this case, we're trying to add it to inputs. Well, let's just say we're adding 2 plus 2, and we see our result equal to 4. This is expecting this is behaving as we expected. So that's great. So then I'll go ahead and switch off the simulation mode. And then I'll click Run to actually start compiling this code for an FPGA target. In this case, what I'll do, I have a prompt that is asking me to build a bit file. The bit file is basically a program that gets downloaded to the FPGA chip, and it's your implementation of whatever algorithm that you're trying to implement on the FPGA. So in this case, it's just an adder. So here basically what's happening is this LabVIEW environment is creating this intermediate files or VHDL files that will get sent to the compiler that will then synthesize a design that will go onto the FPGA chip. So it's basically synthesizing these intermediate files, and then this job will get sent to the compiler that will be able to compile our program. And there you go. Now you'll have, once the program compiles, you'll see an adder implementation on your FPGA chip.